One of the most existential questions in life is, why am I here? I can't answer that question in any real existential way, but I can explain why this course is particularly important. Organic chemistry is largely the chemistry of carbon. Carbon is special because it's able to form such an enormous diversity of stable compounds. These form the foundation of most of the molecules of life and most of the medications, pesticides, fuels, and products that we use. The course tends to be populated mostly with biology majors, so for your reference, you can see that carbon makes up about 18.5% of your mass. But remember, your body is 60% water by mass. If you subtract out the water, carbon makes up almost half of what remains. Understanding carbon chemistry is essential for understanding life. Why is carbon so special? Why do organisms rely so heavily on carbon for essential functions? One of the reasons is that carbon has a wealth of bonding capabilities. Since carbon only has 4 electrons, carbon can make up to 4 distinct bonds. As you've talked about in general chemistry, these can all be to different atoms, a tetrahedral geometry, or one atom can be double bonded, which gives a trigonal planar geometry. Carbon can also be triple bonded to give linear conformations. Carbon bonds to itself or other atoms so stably and has such a wide range of structural diversity that we see lots of possible compounds. Oxygen, on the other hand, only has 2 possible bonds if the oxygen is to remain formally uncharged. We have far fewer options. And on top of that, oxygen bound to itself with a single bond, it really isn't very stable. So we can't really make many molecules that are based primarily on oxygen. We can see the structural diversity available to carbon all through natural biomolecules. Pretty much every type of biomolecule has some form of tetrahedral carbon. But we also see carbon taking on trigonal planar arrangements to make the unsaturation in unsaturated fats, or aromatics in nucleic acids and proteins. And carbon-oxygen double bonds are pretty much everywhere in biochemistry. Fatty acids, amino acids, and proteins, and carbohydrates all feature this carbon-oxygen double bond. Another reason besides structural diversity that carbon is the atom of life is that carbon can bond with itself and other molecules stably. Bond dissociation energies give the amount of energy that it takes to evenly split a bond. Notice that carbon bonds are fairly high in energy compared with many of the other bonds, and are higher than any bond energy for an atom bonded to itself. So even though silicon forms a strong bond to hydrogen and oxygen, it doesn't form a strong bond with itself. This means that we can make large molecular skeletons with carbon in a way that we never would be able to with other common atoms. So carbon is pretty special. In order to see how carbon forms larger molecules more clearly, we are going to quickly review a lot of material from general chemistry, so that we have a firm foundation for understanding how large carbon-based molecules form, and we can use that to form a foundation for the rest of the course. So first off, we need to remember a few things about atoms. An atom is made up of protons, positively charged particles in the nucleus, where they are typically joined with neutrally charged neutrons. The nucleus is surrounded by negatively charged electrons that occupy specific areas corresponding to their energy called electron clouds. Most of the interactions between atoms are actually interactions between their electrons, so understanding where electrons are and how they interact is fundamental for understanding most of chemistry. When we look at the periodic table, it tells us several things that are closely related to the structure of an atom. The first is the atomic number. The atomic number is a whole number and refers to the number of protons in an atom, which also happens to be the number of electrons in an atom, although not the number of electrons in an ion. The atomic number always corresponds to a chemical symbol. Anytime you have the same number of protons, you will have the same element indicated by a 1 or 2 letter chemical symbol. The other number is the atomic mass of a type of atom. This is a calculated value based on the masses of individual atoms and their abundances. So typically comes with a certain number of significant figures depending on the source. The atomic mass depends on the number of neutrons in an atom, even though the neutrons have less to do with its chemical properties and more to do with its nuclear properties. So we give atoms that have the same atomic number and different numbers of neutrons mass numbers to differentiate the same elements but with different isotopes. Mass numbers are properties of particular atoms, not of the element itself, and so again only show up as averages on the periodic table. Most of the time we don't worry too much about isotopes in organic chemistry, but we will see some particular application for isotopes in labeling and kinetic experiments and some types of measurements. A particular interest is deuterium, a hydrogen with a mass number 2, which is so special that we even give it a special symbol of D instead of the H for other hydrogen atoms. The electrons in an atom are always arranged so that they go into the lowest energy space available to them. We call this the Aufbau principle. As electrons inhabit space around a nucleus, they repel other electrons, which are then forced to orbit at a higher energy. We call each of these energy levels a shell. Those shells roughly correspond to the row or period of the periodic table. They always will correspond to the principal quantum number n, which is really just our way of saying that the overall energy level for an electron matches a certain value. Because the space around a nucleus is three-dimensional, electrons can rotate straight around the nucleus, or they can take more complex routes around the nucleus as well. Lower energy levels don't allow for as complex of shapes, which is why there are more columns in the periodic table as the atomic number gets higher. For example, at the lowest energy, only the s orbitals that we can see on the left side can occur, so the periodic table is only 2 wide. That's the section in purple. By the next period, 3 different p orbitals around the nucleus are possible, which we can see in blue, and the periodic table is now significantly wider. With the addition of D in red and F in yellow, the periodic table gets up to 32 atoms wide. The subshells have different widths because there are different possibilities for orientation in space. So the p orbitals that you can see again in the red on the bottom right have 3 different forms, but all have the same energy. We call that degenerate. Similarly, the d orbitals have 5 different forms, so the d block is even wider. The d orbitals here are shown in yellow, which matches the red d orbital section on top. The block corresponding to the f orbitals is even wider, having 7 degenerate orbitals. And you can bet that if we find even more elements past the current 118, we'd have an even wider period, including 9 degenerate g orbitals. So that's crazy. Each one of those orbitals can have up to 2 electrons of opposite spin, but we will always fill up all the orbitals with the same energy before we start doubling up on any. And this is hopefully a good review of the underlying background in electronic structure for general chemistry. The most important part for us is that the highest energy shell of any atom, the valence shell, always is going to have a certain number of electrons. Even though every single element will have a different configuration of its electrons, the valence shells within any column or group in the periodic table are very similar. And since the electronic structure determines chemical properties, that valence shell is really important for us understanding how any group will interact and how any specific atom will interact chemically. We could go through and write electron configurations for each atom, but we get a lot of the same information by only talking about the valence electrons using Lewis dot structures. For example, a hydrogen atom is found in group 1, so it only has 1 electron, which we can draw on the side of the hydrogen's chemical symbol H. This single electron in the Lewis structure gives us some idea of how hydrogen will interact with other atoms by 2 rules. 1, electrons like to come in pairs, so any single electron is likely to form a bond. The number of single electrons generally matches the number of bonds. And 2, atoms always want to fill their shell. The shells of each period are different, so the first shell only has an s orbital and there's a 2 electron max. Hydrogen therefore can only form 1 bond in most cases. We can also fill out the Lewis dot structures fairly easily for pretty much any atom. We only need to find the number of s and p electrons for that atom. So for boron, since it has 2 s electrons and a p electron, which we can see from its position in the periodic table, it will have 3 electrons. We place those electrons around boron, 1 on each of 3 sides. Doesn't matter which sides. And you can see that boron likes to have 3 bonds when neutral, 1 using each of its unpaired electrons. We can also see that boron can easily accommodate another bond and still be within the 8 electron max for atoms that have s and p orbitals available to them. Carbon is just 1 over, so it will have 4 electrons. We draw that in the Lewis structure as 1 up, 1 right, 1 down, and 1 left. Carbon, therefore, has 4 unpaired electrons and therefore likes to have 4 bonds. But because there's no space left over, it will already have 8 electrons. It cannot accept any more once it has the 4 that it wants. Once we move on to nitrogen, we have an extra electron once we've put one on each side, so we begin to pair electrons. Again, where we put the pair doesn't really matter. This tells us that nitrogen, having 3 unpaired electrons, likes to have 3 bonds. We can also see that there's a pair of electrons that's left over, unbonded, that could be shared with something else without breaking nitrogen's octet. For oxygen and fluorine, make sure that you can actually determine what the Lewis-Dutch structure would look like as well. Notice that oxygen will tend to have 2 bonds from the 2 unpaired electrons, but it could still share electrons from a lone pair. Similarly, fluorine tends to have 1 bond, but could, in theory, share electrons from any of its lone pairs as well. Within a group, the valence structure will stay the same, so sulfur's valence shell looks exactly the same as oxygen's, and chlorines are the same as fluorine. What does change is the ability to use d orbitals in bonding. So sulfur and chlorine can actually accommodate up to 18 electrons, which is why some of the ions you might already know, like sulfate and perchlorate, have more than 4 bonds. The Lewis dot structures can tell us about how many bonds are likely to exist for an atom. These bonds are generally covalent. They share electrons. Each bond contains 2 electrons, generally 1 from each atom. Atoms can also double or triple bond, which doubles or triples the number of electrons that are between the atoms, a double bond having 4 electrons and a triple bond having 6 electrons. Atoms can also quadruple or quintuple bond, but those bonds don't typically involve carbon, so that's really just a teaser for all that you could learn in an organic chemistry course. Anytime we have atoms interacting, we can draw their Lewis structures by arranging the atoms and either placing the dots representing bonding electrons between the atoms, or by replacing every 2 electrons in a bond with a line instead, representing those 2 electrons. The negatively charged electrons between positively charged nuclei are not static. The bonds are constantly being stretched and compacted. Push the atoms too close together, and they can't account for the repelling between the positively charged nuclei. Stretch the bond too far apart, and the electrons aren't sufficient to hold the nuclei together. The height of the hill shown with a soccer ball, or the energy that it takes to separate the atoms, is called the bond dissociation energy. We call the distance between atoms that gives the lowest bond energy the bond length, even though the bond length is usually changing back and forth. The bond length is really just the lowest energy point, or the average distance as a molecule vibrates different bond lengths. It's often useful to think of our bonds as springs. The length of the bond is always changing, like if the soccer ball was rolling back and forth between the 2 slopes. As we indicated before, not every bond takes the same energy to break, the bond dissociation energy. We've noticed before that carbon has particularly strong bonds to a wide range of atoms. We can also notice that we have increases in energy of a double or triple bond, essentially a higher hill in our soccer ball analogy. Drawing a Lewis structure for the H2 molecule is fairly simple, but every other possible molecule is more difficult, so it's helpful to have a systematic way of drawing Lewis structures. You've done this before in general chemistry, but I want to remind you of these steps before we move into organic chemistry. We'll also talk about some shortcuts, but you'll always remember shortcuts better if you're able to return to the fundamentals. The first step in drawing a Lewis structure is figuring out how many electrons total that we can use for the structure. Remember that only valence electrons are likely to be bound, so we can simply look at the Roman numeral group number on the periodic table to figure out how many electrons there are. Or we can count the number of atoms we are from the left side of the periodic table using the S and P blocks only. Or if you can identify the number of dots in a Lewis structure, but you can't remember exactly how you do it, it's the same number. So if you can figure out that, you can figure out how many electrons there are for the valence structure. After we figure out the number of valence electrons for each atom in a molecule, all we need to do is add them together to find out how many valence electrons there are in the entire molecule. When we have an ion instead of a molecule, we need to add an electron for each negative charge, remembering that electrons are negative, so anions, negatively charged ions, always will have more electrons for more negative charge. For a cation, on the other hand, we need to subtract an electron for each positive charge. We can use sulfuric acid, H2SO4, as an example for how we do this calculation. The hydrogens each have 1 valence electron, the sulfur has 6, and the 4 oxygens all have 6, for a total of 32 electrons. The next step in drawing a Lewis structure is to write down the arrangement of atoms and draw single bonds between all connected atoms. In many cases, you might be given a formula. Most chemists write the formulas in a way that give hints to the connectivity. Any hydrogen at the beginning of the formula is acidic and is typically attached on the outside atom. The first atom that isn't hydrogen is at the center of the molecule, with atoms that follow typically connected to the center molecule. For example, H2SO4, sulfuric acid, has 2 hydrogens at the beginning, indicating that they are acidic and attached to an outside atom. The next atom given is sulfur, which means that that's at the center. We'll place the 4 oxygens around the sulfur, and then we're going to add the 2 hydrogens to any of the outside atoms, usually an oxygen if available. If the atoms are the same, it doesn't matter where the hydrogen is attached at all. It's common to just write the hydrogen next to an atom to which it's bonded to clean up the structure a little bit. So here we have OH written instead of an O with a bond drawn to an H. It still implies the bond. As a general rule, the central atom is usually a non-hydrogen atom with the smallest electronegativity, meaning you are more likely to have an atom as central as you move down the periodic table and left in the periodic table. So since sulfur is below oxygen, we could also assume that it's at the center because it's less electronegative. After we have the basic structure down, we have to make sure that we have the right number of electrons. We calculated 32 electrons in step 1, but now we've added 4 bonds between sulfur and oxygen, and 2 bonds between oxygen and hydrogen, 1 for each OH, for a total of 6 bonds. Since each bond is 2 electrons, we've used up 12 electrons already, and we have 20 left to place. It's usually easiest to start on the outside and work in, so we'll start with each oxygen. We need to remember that every oxygen will want to have 8 electrons, including the bonds. For the oxygens bonded to both the sulfur and hydrogen, we already have 4 electrons already, 2 from each bond. We only add 2 lone pairs for each of these. On the other oxygens, we add 3 lone pairs for a total of 6 electrons. Combined with the total of the 2 electrons of the bond, we'll have 8 electrons on each of those. Notice that by filling up the oxygen's orbitals, we've used up all 20 of the remaining electrons. In this case, it doesn't matter because the sulfur already has an octet from the 4 single bonds. The structure shown is already a correct Lewis structure. If the sulfur did not have an octet, we would need to move one of the pairs of electrons from an oxygen on the outside into a bond with sulfur, which would allow us to maintain the octet of the oxygens while also increasing the number of bonds to sulfur. Again, we don't need to do this for the molecule shown to get a Wallace-Lewis structure, but we actually can because sulfur can exceed the 8 electrons by accepting electrons into an empty d orbital. The structure shown below has lone pairs from 2 of the oxygens moved into double bonds with oxygen. The oxygens here still have their octets, and the Lewis structure shown on the bottom is actually also valid. Notice that when we made this structure, we moved electrons from the O's and not the OH's, so that every oxygen has 2 bonds. Similarly, we moved a pair of each of the 2 oxygens electrons rather than moving 2 pairs from a single oxygen and forming a triple bond. The structure with 2 double bonds is actually the best structure for this molecule, which we'll see later on in the chapter when we talk about formal charges. Now we can have a chance to work through some examples. I put an abridged version of the steps we just talked about at the top of the slide as a reminder. Our first example on the left is N2, nitrogen. We start by finding how many electrons we have to work from. Each nitrogen brings 5 valence electrons, so we only have 10 electrons. We draw out the 2 nitrogen atoms with a line between, accounting for the 2 electrons. We have 8 electrons remaining, and we'd add 6 of those 8 remaining electrons to one nitrogen to fill its octet, and we'd add the other 2 to the other side. This gives us 10 electrons, so we can't actually add any more. However, the nitrogen on the right doesn't have an octet yet, so it needs to have at least a double bond to increase towards an octet. We can move electrons from the leftmost nitrogen into a double bond to increase the number of electrons available to the rightmost nitrogen. However, when we do this, this still leaves the rightmost nitrogen with only 6 electrons, so we need to move another 2 electrons into an extra bond, now giving a triple bond. Once we have a triple bond, we have an octet for each nitrogen and a valid Lewis structure. Hooray! Working through the next example, we have dinitrogen monoxide. Each nitrogen gives 5 valence electrons and oxygen gives 6. So we're at a target of 16 valence electrons for the whole molecule. When we draw out the atoms, nitrogen is the first thing listed that isn't a hydrogen, so that goes at the center, with the other nitrogen and the oxygen connected to that central nitrogen. Another way of looking at it is that the nitrogen is less electronegative than the oxygen, so that's going to go at the center. We attach the atoms with single bonds, which use up 4 of our electrons, and we have 12 of those 16 left. I'm going to put all 12 electrons on the outside atoms to begin with. That gives me octets on each side, but it leaves only 4 electrons on the center nitrogen. We need 2 more pairs of electrons, so either a double bond from each side, or a triple bond from the left side, or a triple bond from the right side. While all those structures are valid, putting a triple bond between the 2 nitrogens actually leads to the best structure because the formal charges on the atoms, which are actually shown in this molecule, are the lowest. Take a moment and try to work through the other examples shown to make sure that you understand how to create a Lewis structure. Now, check your work against the answers given. If you've got one wrong and can't figure out why, reach out to me for help and we'll work through it together. There are a few types of molecules that tend to work a little differently. Anything with an odd number of electrons is always going to be missing an octet on some atom. There's no way to get an octet on every atom. Anything with boron tends to be shown with only 3 bonds and only 6 electrons. The reality of boron compounds is more complex, but at this stage, we just draw the Lewis structure with only 6 electrons. It's a lot simpler. And as we've already indicated, anything in the 3rd period and beyond can actually accept additional electrons, although they don't need it in every case. So on the bottom you see another example of an expanded octet, something with more than 8 electrons. It's good to be able to draw Lewis structures from scratch, but as you start to get used to drawing Lewis structures, you might notice some patterns emerging. The simplest pattern is that every atom tends to have the number of bonds indicated by unpaired electrons in its Lewis dot structure. Hydrogen has 1 unpaired electron and tends to make 1 bond. Boron has 3 unpaired electrons and tends to make 3 bonds, and the trend continues. This is always true as long as you don't have charges on the atoms and as long as you don't have d orbital contributions from the atoms. If the atom is charged, a negative charge will generally result in 1 fewer bonds. You can see this in the table in the difference between nitrogen's 3 bonds and N- 2 bonds, or the difference between oxygen's 2 bonds and O- 1 bond. For a positive charge, the atoms typically have extra bonds. Nitrogen plus has 4 bonds instead of 3 with a neutral nitrogen. Oxygen plus has 3 bonds instead of the 2 with a neutral oxygen. Carbon, an exception, actually goes down to 3 bonds when it gets a positive charge. And it's different because with carbon, you're losing your octet at the same time. Once you get used to seeing these, this often can make drawing a Lewis structure much easier and much faster. To use an example from before, I know right away for N2O that if I have a nitrogen on the outside of a molecule, it probably wants to be triple bonded if it's going to be uncharged. I also know that if I have a triple bond to the nitrogen, I can only have a single bond to the oxygen without exceeding the nitrogen octet. That would give me 4 bonds to nitrogen on the center, and therefore a positive charge, and then 1 bond to the oxygen on the right, and a negative charge. These shortcuts make the most sense the more problems you do. You'll be able to see the patterns more clearly. Don't try to memorize straight towards a shortcut. You'll lose out. You won't be able to remember and you won't be able to apply it correctly. Instead, as you do problems, try to recognize these patterns in the structures that you draw. If you approach problems that way, you'll learn the shortcuts without trying and on a much better and more retainable foundation.